For nearly a century, theoretical physics and quantum mechanics have built their architectural foundations upon continuous field interactions. Relying on continuous space comes with a structural cost. As these fields interact, they generate intractable thermodynamic divergences, infinite boundaries that break the equations of the classical standard model. The standard response to these mathematical failure states is a process called renormalization. In fields like perturbative quantum chromodynamics, renormalization attempts to extract a finite, measurable prediction by subtracting infinities from infinities. Physicists inject theory nuisance parameters and Faddeev-Popov ghosts to suppress these divergences artificially. The standard model treats infinite physical limits as computational noise, utilizing artificial suppression rather than resolving the underlying thermodynamic divergence. The theory of infinity, TOI, establishes absolute infinity as the foundational ontological primitive of the cosmos. Under this model, the bounded, finite universe we observe is a localized region, organically extracted and configured out of an unconstrained mathematical vacuum. The TOI framework replaces probabilistic likelihood fits with deterministic, number-theoretic topological locks. The execution of this mathematical extraction is governed by the friction versus fiction protocol. If a continuous variable drifts into floating point anomalies and fails to lock onto an invariant structural rail, the system rejects it as non-topological fiction. When continuous sequences attempt to mimic discrete constraints, they generate exact, reproducible logarithmic residuals. This genuine friction provides the mathematical proof of structural reality, representing the thermodynamic phase drag of the universe. Expanding continuous space into higher dimensions via static coefficients creates massive scalar drag. The dimensionally invariant quartic manifold prevents this exhaust by locking the geometric power of the space perfectly to the depth of the spatial dimension. This continuous geometric tension is governed by the defining polynomial of a 4D space, x to the fourth minus x squared minus 1 equals 0. By utilizing identical powers to wrap the continuous dimension, substituting u for x squared, the space collapses into a 2D algebraic generator, u squared minus u minus 1 equals 0. This resulting equation is the absolute minimal polynomial that defines the golden ratio. The golden ratio belongs to an exclusive class of algebraic integers known as Pisot-Vijaya-Raghavan numbers. For any Pisot number, all Galois conjugates are trapped inside the unit circle of the complex plane. Their absolute values are strictly less than 1. The thermodynamic impact of Pisot numbers reveals itself through exponentiation. Confined within the unit circle, as the primary spatial dimension scales toward infinity, the fractional terms of these conjugates decay strictly to absolute 0. This chart graphs the fractional distance to the nearest whole integer for consecutive powers of specific topological constants. As the spatial dimension expands on the x-axis, the decimal fractional exhaust of the golden ratio and the plastic ratio drops exponentially toward 0. Polynomials generating Pisot numbers act as a frictionless scaffolding, allowing infinite continuous scaling without the accumulation of fractional exhaust. Translating that 4D void into the discrete boundaries of three-dimensional Euclidean space requires stepping the polynomial architecture down a degree to match the volumetric container. The universe applies the identical dimensional wrapping, yielding the dimensionally invariant cubic manifold, x cubed minus x minus 1 equals 0. Note that this continuous manifold lacks a squared term entirely. In analytical number theory, this equation is the minimal polynomial for the plastic ratio, the numerical constant that organizes bounded 3D volumetric space. The stability of this space is dictated by Vietta's formulas, which show that in any polynomial equation, the sum of all its roots equals the negative coefficient of the second highest power. Because the cubic constraint defining this 3D universe has a coefficient of 0 for the missing x squared term, the sum of its three structural roots across the complex plane must perfectly equal 0. This complex plane distribution maps the exact configuration of those three roots. The single real root extends right, representing the physical shell of 3D space. Opposite this are two complex conjugate roots, spinning thermodynamic charges, whose combined horizontal magnitude perfectly cancels the outward physical root. This exact cancellation defines the zero-sum double join. The physical material shell is tethered to the geometric origin by opposing inner complex charges, which cancel the thermodynamic noise and yield a stable emergence. To verify if this model accurately maps absolute reality, we test its scale invariance. We must determine if this strict topological constraint holds its geometric conservation when elevated to higher dimensions. We establish a hexadimensional continuous space by locking the spatial depth to a 6th-degree polynomial, x to the 6th plus x cubed minus 1 equals 0. Decompiling a 6th-degree polynomial forces the continuous void into a state of geometric conjugation. The hexadimensional space collapses into two parallel, simultaneous 3D triadic systems, an expanding branch and a contracting branch. Evaluating the complex spatial roots of the contracting branch, defined by x cubed minus the golden ratio equals 0, shows the geometric mechanics remain completely intact. Because both branches lack a squared term, the physical shell remains exactly twice the magnitude of the inner complex charge. The zero-sum double join survives the hexadimensional split. Instead of inventing new thermodynamic rules at higher dimensions, the universe tessellates, stamping the same recursive, self-balancing architecture across every branch of the void. The algebraic topology dictating the final structure interacts with continuous spatial dimensions that exhibit fluid thermodynamic behaviors. Before achieving discrete closure, the unconstrained flow of the mathematical universe erupts as a chaotic bubble in phase space, which must be clamped into a stable laminar column, a Gaussian tube, to prevent infinite divergence. To achieve physical form, this turbulent continuous fluid phase is mapped onto a strict, discrete underlying grid. The framework tests this interaction by utilizing the prime chiral matrix. This matrix acts as a high-stress lattice constructed of contiguous prime numbers whose geometric gaps lack predictable growth. In early iterations of this matrix, symmetric gaps between prime sequences execute dimensional annihilation. The spatial phases physically subtract each other to 0, destroying spatial dimensions to maintain thermodynamic equilibrium. In the deep prime frontier, where prime gaps become turbulent, the matrix stabilizes by forcing the spatial trajectory to lock on to exact Fibonacci integers. This interaction demonstrates the prime matrix acting as a topological sieve, where continuous chaos is forced to conform to the specific boundaries of rigid integers. Operating beneath this dimensional emergence is a bipartite mechanism, the Konrad backbone and the Amanda loop. The Konrad backbone functions as a causal engine, triaging the unformatted potential of infinity into a unified outward flow and anchoring the structural rails of reality to the golden ratio. Bounding this flow is the Amanda loop, which provides the physical reflective force. It geometrically bounces outward expansion back inward to maintain parity balance and prevent the waves from breaching the topological limit. To map these topological constants to observable physics, the framework executes a conditional Lorentz covariant completion. By adjoining the branch-locked TOI states to standard null momentum vectors, the framework explicitly equates these geometric limits to the physical transverse photon sector of free Maxwell theory and covariant quantum electrodynamics. Observable physical reality manifests as an exact covariant projection, constrained by immutable, frictionless polynomial law.